Hi everyone, it's 11:30, so I'm gonna get started. My name is Steve. I work on the Rust project at Mozilla. I'm not gonna talk about me a whole lot today because that's boring. I'm here to talk to you about Rust in production. So this is not really an introduction to the language, although I'm gonna start off by showing a little bit of stuff about the language. Who here has actually used Rust before, just so I can get a vague idea? Cool, so some of this might be a little bit of a review for some of you, but not too much. So first of all, I'm going to talk about what Rust is itself, because part of the question here about like Rust in production is what does Rust actually offer? Like why would I want to use Rust in production? So I'm going to talk about that stuff first. And then there's actually sort of an interesting question, which is what actually is production use? I think that this is a sentence that we say, like, is X ready for production? But I think that it's actually a much more complicated question than those simple words indicate. So we'll talk a little bit about that. And then finally at the end, I'm going to show you some case studies of companies that have been using Rust in production or are about to, and talk about like their successes and I don't want to say failures exactly because that's been relatively minimal so far, but you know, I try to be a little balanced about things. So this is sort of the summary of what we're going to talk about today. Also, I know I'm standing between you and lunch, and this slot is a full hour, but I tend to talk fast, so I think I'm going to go a little bit under, so you can beat everybody to the line for lunch stuff. Okay, so Rust. We describe Rust as a systems programming language that focuses on safety, speed, and concurrency. And the big problem with words is that nobody knows what they actually mean. So all of those four words that I've bolded, which this font is not that great for bolding actually, this typeface is not that great for bolding. So systems, safety, speed, and concurrency are the important parts of this thing. So I want to talk about what those four things mean because those mean different things to like everyone. So the first is systems programming, and this term is incredibly, ridiculously overloaded amongst a ton of people. And this is a particular version of this definition that I really like, and this was coined by Yehuda Katz, as far as I know, and that's when the details matter. So systems programming is any time when you need to care about the details. I come from the Ruby world previously, and one of the things that we really commonly say in Ruby land is like, Ruby is slow, but that doesn't matter because the network is the bottleneck. Ruby uses a lot of memory, but that doesn't matter because memory is cheap, all that kind of things. But the problem is some applications, memory usage does actually matter, or the speed of Ruby is actually a problem. And that doesn't make Ruby a bad language. That means that Ruby is good for certain kinds of things. And so Rust is the kind of language where if you need control over any sort of aspect of your program or execution, Rust will give that to you. And so specifically, a lot of the reasons that people reach for a language that gives them this kind of control is on these kinds of details. So for example, I need to deal with exactly when my memory is allocated or deallocated. Our garbage collector is too inefficient for my use case. I need to be concerned about the exact memory layout of what's going on. This is really important for our performance. Even as computers get faster and faster, cache is still a thing. Being able to fit your data into L1 cache is like significantly useful for speeding things up. Making sure that things can be vectorized is really, really important. So having control over memory layout is definitely important for performance in general, but also generally speaking, like control and performance go hand in hand. So that's like a big reason why people care about these sort of details. And then just general sort of determinism. I'm going to click on this little link. We have this really cool thing called the playpen. I'm going to close my Twitter tab. So I want to show you a teeny little bit of Rust code. This is a really cool play.rustlang.org is a website where you can type in Rust code and then hit run, and then it will run. And you can also like see the assembly that it generates, and you can share this with other people and stuff. So it's just one example of like how this works. Here, let me make this teeny little bit bigger. But again, it's not really about the code that much. So one more smaller. Okay. So I have a structure here that's a point, and it's got an x and a y that are both 32-bit integers. And then in my main function, I make a new point called origin, which has x and y set to 0, because that's what the origin point is about. And then I move that point onto the heap by using the box new construct. So the things that I want to point out about control in this kind of example are this is a structure in the sense that I can know for sure that this will take up exactly two 32-bit integers worth of memory. There's no extra metadata, there's no like object here, no like vtables, none of that kind of stuff. When I declare origin in this way, by just declaring a point, it is stack allocated by default instead of heap allocated by default. So like everything is always on the stack, and I need to use something like a box if I want to explicitly heap allocate things. Furthermore, I know that whenever the main function is over and these two variable bindings go out of scope, that is exactly when this memory will be deallocated. So there's no garbage collector here. We're using the C++ people call this RAII, which is like a terrible acronym, I think. So we sort of like say ownership and borrowing, but again, this is not really a Rust tutorial. My point is that like everything here is deterministic, and I can tell you exactly how much memory it's going to use and in what way it's going to use it. Okay, now I need to click on this present again. Yes, success, got back. Another thing about this that I think that people don't necessarily appreciate with this kind of control, but is something that's become very important for Rust, and I'm going to talk about this a lot later in the case studies, is that another thing that system-style programming gets you is playing nice with other languages. So a use case that's becoming incredibly common in the Rust world is putting Rust inside whatever other language you are already using. And if you have a language that does not give you that degree of control, say you have a language that is garbage collected, because Rust is not garbage collected, if you want to embed that language into another one, now you have two garbage collectors that are fighting with each other over what part of memory is happening, for example. So a language without GC is significantly easier to embed into a GC language, and just in generally speaking, like has lower requirements and is significantly easier to put inside of other languages. And so we're seeing this as being a very, very common way that Rust is being used, is like I write most of my app in language X, but then when I need this particular part that needs a little bit of extra oomph, I drop down into Rust. Whereas historically, people might have said you drop down into C. And I'll get into why that's a viable and interesting option in the case study stuff. Okay, so that's system stuff. Next up is safety. And this is a thing that is always brought up when it comes to Rust, and it's also something that's like tough. And the reason that it's tough is from the, like basically marketing is hard. So from a programming language theory perspective, this is a part that's interesting to Rust. But for people that aren't programming language theory nerds, this is a part that a lot of people don't necessarily like intuitively understand why they need this particular thing and what we guarantee around safety. But the biggest difference that Rust makes is that it is a safe systems language. So in this particular case, what we mean by safety is memory safety. So even though Rust has no garbage collector, at compile time, Rust guarantees that you will have no segmentation faults, you'll have no dangling pointers, and no iterator invalidation, amongst various other kinds of things, but these are three of the most common things. And so when I said earlier that performance and control kind of go hand in hand, there's this dichotomy that has happened in programming languages, and this has usually been true, where you can either have a language that is memory safe and usually has a garbage collector, and so therefore it is safe but significantly slower, or you can have a language that gives you a ton of control but then is very dangerous. So there's like an old joke that C++ is like a bazooka that is already pointed at your feet. That's like, you know, it is dangerous, and C is also dangerous, and sharp tools are very useful, right? Like if you're a chef, you want a sharp knife, not a dull knife. But this analogy sort of falls down, or at least Rust is trying to make this analogy fall down by having the safety of a language that is garbage collected while having all of the degree of control that you have over a language that does not. So I have two code examples here to show off the way that two of these things work, but the important part here is that they're at compile time. I'm going to get to that part in a second. I'm going to show you these two things. Okay, so here's our point again, and then there's this main function called won't work, and what this function does is, I can't scroll a little bit farther, so it's still going to be on the bottom. Let me see if I can get, there we go. Okay, so this function tries to allocate a point on the stack and then return a pointer to it. And so this is a very trivial example of what's called a dangling pointer. So if I wrote this code in C, the origin is going to go out of scope at the end of the function, and it will disappear. So now this pointer is pointing to invalid memory. And so accessing that pointer is now undefined behavior, and all sorts of bad things can happen, or might not happen. Like that's actually, so part of the problem with undefined behavior is that it might do something reasonable for a while, and then only eventually later do something terrible. You just have no idea. But if we try to actually run this, Rust will complain. And in this particular instance, this gives us an error that is, I'm going to shrink this a little bit. It says this function's return type contains a borrowed value, but there's no value to be borrowed from. And that is basically saying this is a dangling pointer. It uses a little bit of jargon that I have not fully explained to you because, again, this is not about being a Rust tutorial. But my point is that this kind of unsafe like code just straight up does not compile. So you have to actually, if it compiles, it works is a little too strong. People like to use that phrase, but that's not always true. Software has bugs. The Rust compiler is not perfect. Static analysis is inherently conservative, but there's a significant amount of work that is required in order to get through. I'm going to click on this other one, through the compiler and make sure that code works properly. When I'm not in presenter mode, this does not actually do the right thing. Okay, so here's another example of Rust statically preventing a problem at compile time. So if I have a vector v that is mutable and it has 1, 2, 3, 4, 5 in this list, if I loop through each element in the vector, getting references to them, so I'm getting a reference to the first element and the second element and the third element, and then the line 5 there prints out this element is E. This works, but line 6 is the problem. So v.clear empties the vector. So if I modify this vector while I'm looping over it, that means that all of the other indices are going to be invalid, and that's a problem. Different languages handle this problem differently. It depends. If you're using Java, Java will say, hopefully we will throw a concurrent modified exception, but it's not actually guaranteed. If you run this in Ruby, it will give you what is intuitive to people that understand Ruby's GC, but not intuitive to humans result. JavaScript will also happily execute this code and do stuff. And C++ will be undefined, or C also will be undefined. But in Rust, this gives us a compile time error. And it says, cannot borrow v as mutable because it's already borrowed as immutable. And this whole big error message, which basically points out, hey, you're already referring to this vector here, so you can't also mutate it while it's being referred to. So again, this is like a static compile time analysis. There's no runtime overhead for doing this, but it catches a lot of errors. And both of these two examples are really trivial versions of this problem. One of the problems with trying to show off analyses like this is that, for example, the first one, GCC will warn in like trivial cases like that, but this analysis is significantly more sophisticated and will catch all of the cases as opposed to just the trivial ones. So, okay. Bam. And I guess this also then ties into the next one, which is speed. So you'll also notice that speed is the second goal. It's safety and then speed. So Rust wants to be extremely fast, and it does for reasons that I'll get into in a second. But the point is that we always do the safe thing first and the theoretical speediest thing second. But through the wonders of programming language design and LLVM and optimizing compilers, it turns out that the safe thing is often also the fastest thing. So I want to preface this slide with I absolutely love and hate the benchmarks game. The benchmarks game is both terrible and wonderful, but right now I'm near the top of it, so I'm putting it on a slide. Basically, it is really, really important to understand that when you do micro benchmarkings, I think one of my favorite descriptions of the benchmark game, for those of you who are not familiar, it's basically a collection of 10 or 15 programs that people submit things to, and then they're on this chart. And I think that it's important. Someone described it as like, it's really testing the speed of whoever has the most free time on their hands for writing the benchmarks. And then also in the case of the benchmarks game, it depends on who is convinced the maintainer of the benchmarks game that their program is like an acceptable one to include, because he sort of arbitrarily decides like this is cheating versus not cheating. But the important part is not specifically like that. So in this instance, for example, so there's columns that indicate which programming languages. The leftmost is the fastest and the rightmost is the slowest. The left is GCC with C. The second one is Rust. And the third one is C++ with G++. So the important part to me here is not like strictly speaking that Rust is beating C++. The important part is that Rust is comparable to C and C++ in terms of speed overall. Like, obviously, your application is probably not figuring out n digits of pi or like the Mandelbrot set. So like this may or may not be like directly reflective of your application, but this sort of points out the degree to which we are able to optimize Rust code and the degree to which we have made language decisions that do not inhibit optimizations. Because Rust being very, very fast is really important. And in our production users, I will talk a little bit specifically more about why. But yeah. And so this is sort of just a general kind of rule. Rust should be roughly the same speed as C or C++. If not, as a bug. There are lots of bugs, so like please file them if you use Rust and find them. But this is sort of the like mental takeaway in terms of thinking about language performance that I want you to have in your brain, is that Rust is in that class of languages, generally speaking. Okay. And then finally, concurrency is the last part of this. I'm not going to show any code for this because this is complicated, and I promise this would not be an introduction to Rust talk. But what's interesting is that concurrency sort of, it was always a sort of core feature of Rust, but is now actually serviced through the type system as opposed to like the language itself, which is interesting and complicated, and is also a whole talk that I give entirely separately of this. So to give you the summary, there's this slogan called shared mutable state is the root of all evil. I'm sure you've all heard of this problem. But what's interesting about this particular quote is that most languages interpret this as being mutable state is the root of all evil. But it turns out like mutable state is not actually the problem. You can also look at this quote and take it as shared state is the root of all evil. And like that's not actually, strictly speaking, the problem either. The problem is like shared and mutable at the same time is the root of all evil. So if I have immutable data and I share it across n threads, that's totally fine because they're all going to read the same value every single time. If I only have one thread accessing a piece of data and it's mutable, that is totally fine because no other threads are going to be able to observe the problem here. And so most languages deal with this problem by saying like, okay, to deal with concurrency, we're going to make everything immutable and then try to figure out how to make that perform in a reasonably acceptable way. What Rust does is a little more complicated in some ways, but also not. And so basically, Rust will let you share immutable state as much as you want, and it won't let you share mutable state unless you specifically use some sort of concurrency primitive that provides you safety. So Rust does not take the position that like, for example, shared memory concurrency is bad. We just have a type system by which you cannot do shared memory concurrency unless you put it behind a mutex. The type system will actually not let you. So you can't accidentally stumble across these kinds of shared mutable errors. And again, the way in which we accomplish that is a thing I would love to tell you about, but is not what this talk is actually about. But the important part is that like concurrency is very important to Rust. And again, this is sort of a little miniature theme you may have noticed. I mentioned that it'll give you compile time errors about concurrency, and that's actually true and kind of mind-boggling at first, is that this is not like I run my Rust program a bunch and monitor it and then check the errors that come out. This is at compile time, the Rust compiler will say, hey, you are sharing this data between two threads without a mutex, that's wrong. So anyway. It's really, really cool to have. Now when I write Ruby code, I am terrified that I'm doing the wrong thing because I'm so used to the compiler checking everything for me that I'm just like, I'm allowed to do whatever I want, and that's really scary. I also just turned 30 and I'm slowly becoming a real adult, so maybe that's part of it as well. Okay. And then so the last thing I want to mention before I start getting into the production aspect of this talk, which is theoretically the point, there's this tension that I have not totally been able to resolve in my like marketing Rust to people efforts, and so I want to just present you with this conundrum so you can think about it yourself. One of the weird problems about Rust is that there are an equal number of people who say Rust is a high-level functional programming language and people that say Rust is a C replacement. And the problem is that like they're both right, but in different ways. And so there's this issue where I want to communicate to you that Rust has absolutely all of the low-level capabilities that C does, and is able to do all the low-level things that C does, but is not a pain to use in the way that C is a pain to use. And so when I tell a lot of people like, oh yeah, you can use Rust as a C replacement, they're like, cool, I never use C for a good reason, so I will never check out Rust. And so this is like kind of a problem, because if I talk about Rust's high-level features and it being awesome and easy to use, people assume that it is not good at low-level stuff. And so this is just kind of generally a problem that we have about how to like properly get across this message. And historically speaking, because we sort of come from the low-level systems-y space, we've tended to focus on the low-levelness of the language, but I think that drives away a certain class of users that would like happily use Rust otherwise. I also call this the diesel objection. So my friend Sean writes this ORM called diesel for Rust, and he gets mad at me every time I talk about Rust being low-level, because he's like, that's totally irrelevant for my use case. I do not care about this. Sean is a database guy. And so he is writing an ORM in Rust. And so this is some Rust code here on the left. The idea is that it's sorting a certain number of versions that belong to a crate. A Rust package is called a crate. So this is like talking about like package management or whatever. So if we're writing that we want to see the versions that belong to a particular crate, and then pick one that matches an ID and order them and do a limit and then filter based on various things, this Rust code generates that SQL code, which if you're not super into SQL, like whatever, you don't know the difference. But the thing that I think is really cool, that again I'm going to leave totally unsubstantiated because this is not a talk about diesel, is this Rust code is actually faster than if you typed that literal SQL into a string and sent it to the database driver. In general, Sean believes, and has some benchmarks that demonstrate this so far, that using Rust to access Postgres will be significantly faster than using C to access Postgres. And there are a number of reasons why that is true. They all basically boil down to types are really cool, and type systems let you do a lot of stuff. But so he is always like, you should not talk about the low-level aspects, you should talk about the expressiveness of the type system and how it lets you like double-check your work and all these other things. So he's who I always think of with that respect. But anyway, so I'm sort of two minds about this. Okay, so that's enough background stuff about Rust in general, but I needed that to set up, like, to motivate these particular production use cases. Before I actually talk about the use cases, I want to talk about what it means to be in production anyway. I think it's really important that you understand that is X production ready is a question that needs additional context in order to be answered. Now, it's my like pretend English major background to say, well, everything is contextual, of course. But like, I think that this is really important, that this particular question, like when I was writing this talk, I was setting out to answer the question, like, is Rust production ready? And my answer is like, yes, but it depends, which also incidentally is, I think, the sign of a good engineer, is that you always need to have a but it depends, right? Like that's because every single thing has trade-offs. So I don't want to present to you like, this talk is not about like Rust is absolutely ready for everyone and you should use it today for literally everything. If I was telling you that, I would be a liar and deceiving you. So who here is familiar with this diagram? This is like an old thing. This is from this book called Crossing the Chasm. For those of you that have heard of it, this will be a little bit of a review, but it seems like a lot of number of people have not. This was an old business book about how businesses and technologies get adopted. And basically the idea is that if you take the subset of users of your thing, they fall underneath this curve. And so we can split the curve up into five different like groups of people, basically. And that's all good and fine. But the thing about the book is that there's this chasm there, hence crossing the chasm. And what the chasm represents basically is that there's no actual guarantee that just because some early adopters like your thing will actually get used by a significant number of people. Because there are a lot of technologies and businesses and products and whatever else you want to apply this to that will have a lot of people who are very enthusiastic at the beginning, but will fail to reach sort of the mass market or the mainstream market, as this particular version of this chart displays. And the reason why is that there's this gap between a lot of the early people who are involved and this group of people called the pragmatists. And so your like goal as a startup, which is the context in which I originally wrote this book, or as a technology advocate or enthusiast or whatever, if you're on the left-hand side of this chasm, your goal is try to convince the right-hand people to use this thing. And so what's interesting about this analogy, and I love it, and I use it to think about all sorts of stuff. Like, for example, I think that a lot of people arguing on the internet boils down to one of them, like, if we're talking about a technology, let's just say Node.js, for example, I think that a lot of people arguing about, like, Node.js is awesome, Node.js sucks, is because one of the parties involved is in the conservative part of this when it comes to this particular technology, and the other person is part of the visionary section. And so they're actually talking past each other because they don't even have the same goals in the first place. So I think this is a really important concept. But anyway, I think that a lot of people, when they're talking about is it production ready, is what they actually mean is the technology here? And like by here, I don't necessarily mean like used by the pragmatists. I mean like you can sort of split this down even farther, and I think a lot of people would like to think of themselves as being like before the thing, but they want to wait until after the thing is successful, but not too long after. Because if it's too long after, it's not like cool anymore. So you want like the benefit of it being like just freshly over the chasm, but not like so much that those boring conservatives and skeptics might think that you've made a right decision instead of a rash decision, right? Like we all want to be a certain degree of cool. And so to me, I think that especially when it comes to something like a programming language or an open source technology, the chasm is the question of is this ready for production or not? And so there are certain people who will start using something in production when it's on the left edge of the chasm, and then the goal is to get enough of them to start using it in production that it has reached the right end of the chasm and has now crossed it. So, like, I think that that's the actual, like, this is the test. And so, of course, obviously, the follow-up is I think that Rust is at this part of the chasm. You may or may not agree or disagree with me, and that's fine, but I definitely don't think that we're like in the middle yet at all. But I think that Rust is sort of in this point where we are either in the chasm or just barely on the other side of the chasm. And the reason why is that we do have a number of significant organizations using Rust, and so I would like to tell you about them. So here is my set of case studies. I have 4 specific examples to share with you of varying degrees of production use of Rust. And this is my first one. This is a logo of a company called MadeSafe. They do this thing that, depending on how you look at it, it's either like a way to save your files on hard drives securely or a cryptocurrency based on how you look at it. It's complicated, but like I actually don't care that much specifically at what their product does. I do care about the experience they had when using Rust. And they are also like, they've received like $20 million in VC funding, and there's TechCrunch articles and whatever if you like care more about this topic and learning what they did. But what I think is interesting is their particular story. So MadeSafe was a C++ shop. They have like 10 or 12 developers working full time, C++ experts writing tons of C++. And they sort of had this version 1 of their app, product, whatever it is, network, future of the internet, as they like to call it. And it was 750,000 lines of C++ code. And the reason I like this story is because most of the time people would say like, but then you would expect me to say, if I told you this company has a big C++ code base, they rewrote it in Rust and it got a lot smaller. But like the problem with stories like that is that every rewrite ever always gets smaller because you like know the problem better and you can get rid of all the vestigial stuff that you weren't using and all those kinds of things. And so what I like about this particular story is they decided to do sort of like a version 2, and that turned out to be the same amount of functionality but in 75,000 lines of C++. So they sort of like saw that own recognition by rewriting the same language. And then basically what happened is their CEO heard about Rust, thought it might be kind of cool, and said, I have some spare time this weekend. What would happen if I rewrote one of our components in Rust this weekend? And then he did it that morning. And he's like, OK, I'll do another one. And then another one. And then like 2 weeks later, they had rewritten the entirety of the 75,000 lines in 7,500 lines of Rust code. which is again another 10x reduction. These are the numbers they gave me. I do feel that the orders of magnitude being this exact feels a little weird. I'm just reporting the news. But I think that also part of the reason why you get this 7,500 line number is also significant. And the reason why is cargo. So one of the things that I did not tell you about Rust yet is that we have a package manager / build system thing called cargo. And Rust packages are called crates, so you use cargo to ship your crates between people. Like, cutesy. You know, I don't know, I like it. It's got a very like blue collar, like dock worker feel to it. But the important part about this is that in that 75,000 lines, the reason that it's only that small is because they found a number of open source packages that were already available to use for them. So that's not counting the lines of code of the packages they used, but the point is that when you're writing a large C or C++ application, because it does not have a way to do things like dependency management, you tend to look at yourself in the mirror and go, do I use a Git submodule or do I just write the damn thing myself? And it seems like a lot of people choose to just write the damn thing themselves because like maintaining an upstream dependency using makefiles and Git submodules leads to crying, in my experience anyway. And again, I'm not necessarily the best C++ programmer in the world, so maybe it is a personal failing of mine, but every time I use Git submodules, I rethink my life decisions. As much as I love Git, Git is like one of my favorite tools ever, but submodules are terrible. I didn't do my normal little spiel about, I like to talk about there's 3 communities that sort of come to Rust. There's systems programmers, the functional programmers, and the scripting programmers. All of them bring something to the table, and all of them like get something out of Rust. The big thing that the scripting people, who I nominally consider myself a part of, what we bring to the table is a respect for user interfaces and making tools that work well. So like a couple years ago, you would still use makefiles to write Rust code, and then a pile of us Rubyists joined and were like, we like bundler and NPM and these kinds of tools. We want one of these for Rust. And all the systems people said, okay, you cute kids, do your little kid thing. We'll be here like adults writing makefiles. And then we wrote cargo, and then they went, oh my God, why am I still using makefiles? So what cargo lets you do, again, is like if you're from the systems world, it's sort of new, but if you're from the Ruby world or the JavaScript world, it is very boring. Basically, there's this website, crates.io, and it gives you these list of packages. I think that I made another, no, I did not. Basically, like all you need to do to get a dependency in the Rust world is to add 1 line of configuration to your config file. I'm supposed to have questions at the end, but I guess if you have something that's relevant right now, I can do a thing.
Well, I was just going to ask if cargo has left pad.
So the question is, because I have a microphone, is if cargo has left pad. The answer is it has 3 left pad packages now. 3 weeks ago, it did not. It had 0. It does. My partner actually works for NPM doing community management, so this question has been near and dear to my soul for the last couple of weeks. Anyway, the important part is the difference there, I'll just shout that out in the moment. Cargo is immutable, so you cannot unpublish things, so that will not happen. The left pad thing cannot occur with crates.io. You can mark a package as no new dependencies are allowed, but it is append only and immutable, so you cannot destroy the entire ecosystem because you get upset. That doesn't work. But the important part is that by reducing the friction of writing open source code and sharing it with other people, it happens a lot more often. I'm going to talk in a minute why this like 34 million downloads number is like a little questionable. Actually, well, yeah, I'm getting to it later. But it is a lot. It is actually that many downloads, but part of that is due to bots. But the important part is like we already have 4,600 crates in stock. I took this screenshot a couple hours ago, so this should be like roughly accurate. There probably are like 3 more or something by now. But even as a relatively young language, because we had this ecosystem tooling available beforehand, there is a significant number of people writing these packages and sharing them, and for all kinds of domains. So I actually have a hobby project that's, the pitch is, you know JavaScript, let's write an operating system in Rust together that I'm currently working on. it's actually more feasible than you would think. It turns out it takes about 150 lines of assembly to boot up an x86 machine, and then you get into Rust code and you just write some Rust. The important part that's really cool is, while I am writing this build a Rust OS tutorial, there are actually packages on crates.io that are useful when writing an operating system. So like the idea that we can like share code when writing our own hobby OSs together is like very, very new. Like most of the times those kind of projects have no sharing whatsoever and again are written entirely separately. Like there's a package that lets you access features if you're using like a specific model of x86-64 CPU. You can like get the specific assembly like whatever shenanigans. That's not the point. The point is that we are small but growing in this department, and that's one of the reasons why MadeSafe was able to do their job so quickly, is that there are a significant amount of things that are already done for you and it's trivial to use them. And so one of the things that MadeSafe has said a couple of different times is that they think that they are like now, so they rewrote everything in Rust and they've thrown away all their C++ and they do everything in Rust nowadays. It's been about a year and a half, I think, since they've done that. And they're like, we're already farther along with our project even though we did a rewrite in Rust. So they were concerned about their velocity, but they think that using Rust has actually made them be able to go faster. They specifically have this story about one component. I didn't find a good quote about this because it's sort of long, so I'll just leave this slide up while I tell you it. But there's this one particular component that they have renamed Crust since they rewrote it in Rust. It was called something else before. But it basically does routing, like IP routing of packets to different computers doing stuff. And they spent about 6 months when they wrote the C++ version debugging memory safety errors around random seg faults and other things that were occurring in their code. And they've never had a seg fault in their Rust code ever. They're like, we wrote it in a weekend and now it just works and has worked forever. And so that's what they mean by like, we are more productive in Rust than C++, is this kind of static analysis shenanigans means that you don't spend hours and hours debugging scary bugs later, basically. Okay, enough about cryptocurrencies. Let's talk about Dropbox. I don't know how many of you have heard this news that came out relatively recently. I'm really glad that it happens a couple weeks ago. They finally announced it. But there was this story that was going on in Wired, specifically called The Epic Story of Dropbox Exodus from the Amazon Cloud Empire, which is a little dramatic, but I guess it's hard for magazines these days, so you gotta have people buy them somehow. But this story was the first public announcement about Dropbox's use of Rust in production. And what's cool about it, so this is 3/14/16 is what the little date says up there. So just a couple weeks ago they announced it. But the cool part is that they had actually turned on their Rust code in the middle of December, and nothing bad has happened yet. So they like wanted to wait a little while. So like we knew that they were working on this project, and we had talked and helped with them with certain things for a while. And then they had finally told us midway through December, like, hey, we're putting the Rust thing into production for real today. I'll tell you about what it is in a second, but well, I'll tell you right now. Okay, so basically, Dropbox's core business proposition is storing some bytes on some hard drives somewhere in the cloud, right? Like, and then you want those bytes on another computer, and they magically appear there through no work of your own. That's like their business. So that involves a whole lot of different stuff, but like at the very core of it is what bytes go on which hard drives and how do they go there. And so they rewrote that component of their stack in Rust, the absolute lowest level layer of the server-side hardware stuff. And so what they did was in about September, they finished implementing it, but they turned on 2 versions. So they had like their working code and this brand new rewrite, and they monitor it for like 3 months until they were confident that it worked well enough to be okay. And then in December, they turned it on for real. And so now in March, they finally announced this is like a thing. Yeah, so I'm really excited about it. There's only really been this story so far, but if you pay attention in the coming weeks, they're going to be doing a like 12-part blog series about it or something. I don't know. Marketing wanted them to get the Wired article out before their engineers were allowed to post on the engineering blog about the engineering stuff. So they've said that they're going to have a number of posts about all the aspects of this thing, including 2 or 3 that specifically focus on the use of Rust. But I just wanted to comment tell you some of the comments that they have said about their usage of Rust. So again, about 18 months use in total in production as of December. Stability has been very good. In the last 6 months, we've had no issues with the stability of the compiler, the binaries, or the standard library. Long story short, we have a very short list of minor grievances with Rust and a very short list of major ones, which is basically build times. But in general, it's worked out really well, and we're seriously investigating writing more Rust for pieces of our infrastructure at Dropbox. So I'm like really, really excited that they are happy with things overall. The build times thing is interesting and complicated, but like we're working on it. The thing that's funny about build times is it depends entirely on what you do that determines whether it's fast or slow. So like I hear some people say Rust has really fast build times, and then other people say Rust has really slow build times. Dropbox is mostly a Go shop, so any build time is a slow build time to them. And that is not to say that their grievance is not legitimate, but like we're working on making it significantly faster. But part of the problem with having a language that does significant amounts of static analysis and optimization is that means build time. Like fundamentally, you can't escape that. But we don't want it to be a pain point, so it is being worked on. Yeah, so they've been having a good time, and I'm glad about it. I think this is my stability slide. Yeah, stability. So Yehuda Katz, who is also a Rust core team member, I mentioned him earlier with his systems programming thing, quote, he gave a talk yesterday that was really fantastic, and I think it got recorded. I hope so, because I want to link it to people, called Stability Without Stagnation. I don't know if any of you saw that particular talk. And he referenced Rust a couple different times in this talk. But basically, I think that Rust is one of the programming languages that takes stability extremely seriously. And this has a number of different components. One of them is basically we have the without stagnation part is the interesting part. So stability does not mean we never change. It means we ship things to you regularly, but we also guarantee that they do not break. So as a programming language, we actually have a 6-week release cycle. And the next version of Rust is actually coming out tomorrow, day after tomorrow, Thursday. And then 6 weeks from then, the next version of Rust will come out. And 6 weeks from then, the next version of Rust will come out. Which normally frequent releases are associated with instability. However, there's a number of reasons that we actually believe that leads to stability. So I will give you an example from Ruby world again, because I am from Ruby and love Ruby and have a Ruby tattooed on my body, so I criticize it from a place of love, not a place of anger. Ruby releases on Christmas every year, traditionally. That's the Ruby release day. And one of the problems with having a yearly release is if someone proposes a new feature in October, you're looking at either like we hurry up and sneak it in, or it's going to last another like year before it gets in. And so one of the problems with having a long release cycle is that you feel this pressure right before the release to like get stuff in before you're ready for it to go. And so by having frequent but smaller releases, it's totally okay if a feature is not going to be ready for the release on Thursday, because it will be 6 weeks until the next release, so it's totally fine. So this actually encourages us to ship major things on a longer scale, because we don't have this pressure, because releases are kind of boring. And so there's that kind of like software engineering aspects to it. There's a whole host of stuff. Again, Yehuda literally talked about this concept for an hour, so I don't want to like use my entire talk to talk about this talk in general. But there's one thing that he did not talk about because it's sort of Rust specific, and that's and a shout out to Crater. So remember that I told you that 34 million number was like a little sketchy. One of the things that we do on a regular basis is we download literally all of the packages and try to compile them. So we actually have a tool. So the release is coming out on Thursday. The branch actually happened yesterday, and we're currently in the process of like building the release artifacts. But before we did the branch, one of the things that we did was we took what will become the next release of Rust, and we ran it across literally every single package in the ecosystem and determined that all of them still worked. So we can actually like guarantee you that when the new version of the language comes out, everything will be fine, because we already did it. And in the working up to the actual release, like we don't do it every week, but we do it on demand whenever we have a change that we think is like significantly suspicious. Like, does it refactor a lot of compiler internals around the type system? Probably better double check that we didn't break anything, and all this other kind of stuff. We also heavily test Rust itself, and we actually do full continuous integration. So like no commit lands on master without having run through a ridiculous array of tests. We actually have 36 separate configurations of platforms that we build for and on to double check that they all work. And as of last week, on every commit, we download the top 70 of these packages and check that they're okay on literally every commit. So we care a lot about stability and making sure your stuff doesn't break, even though we do this sort of rapid release kind of thing. And so that's why that number gets a little inflated, is because like we're sort of doing it a lot. But S3 can handle it. It's built for, we're just tiny in the giant bucket of the Amazon cloud. But yeah, so we do a whole bunch of checking to make sure these things work really well. And one unfortunate side effect thing of this is that in a language that's statically typed, almost any change can be construed as a breaking change, right? Because like if you add a new function to something, a new method to an object of, well, we don't strictly speaking have objects, but whatever. If you add a method to a struct and somebody else has already defined a method with that name, that is technically breaking. So we have sort of rules about when we are allowed to make changes that would be perceived as breaking and how all that stuff works. And we, on each release, we call out like, here is a change that you may need to make a small tweak. But basically, if it takes more than 5 minutes to fix, it is not considered acceptable, is sort of the general rule. But statically typed languages make it really, really hard to change literally everything. And even languages that historically take breaking changes very seriously, like Java has a reputation for not ever breaking your code, but every Java release has breaking changes. They're just so minor you don't notice them. So that's our goal, is to, you should never notice breakage in the ecosystem. Okay, and now I want to talk about Skylight. So a little slower, lower resolution than I had hoped for this logo, but whatever. Skylight is one of our oldest production users and probably one of our first production users overall. And what they do is they are a performance monitoring tool for Rails apps. So what happens is if you have a Rails application, you gem install Skylight, you sign up for an account, you add your private key or whatever to your app's config, and then it basically monitors everything and sends the data back to their servers, and you get a little web app that you can like check out, like these are my slow pages, this is what's being fast or slow, yada, 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 this kind of stuff. And so what's interesting about Skylight is that it is a Rails app, so you need to install a Ruby gem to make their thing happen, but that Ruby gem is actually written in Rust. So this is the embedding case that I was talking about earlier. The initial version of the Skylight monitoring gem was actually written in Ruby, but there are two problems. One is GC pauses plus performance monitoring is complicated. Did your app receive a sudden spike in latency because a bunch of people hit it, or because the GC decided to start working while you were in the middle of timing? I don't know, etc. There were also sort of memory leaks, and Yehuda, who co-founded Tilda, which makes Skylight, literally has commit to Ruby, and he could not find the memory leaks in that Ruby program, so it's hard. And so due to like the speed issues and the memory leak issues and a number of different things, one of the other co-founders of the company said, excuse me, let's rewrite the gem in C++ technically, but you know, whatever. And they did it, and then they thought long and hard, and they remembered that if a Ruby native extension seg faults, it brings down the entire Rails app. Like it doesn't just isolated crash, it just crashes the Ruby interpreter and everything that goes with it. And they thought, we're about to ship this code to thousands of people on thousands of servers that we don't control and we can't ever log into or monitor in any way. Are we actually confident that this will never seg fault under any of those adverse conditions? And then they said, maybe this Ruby thing isn't so bad after all. But then they heard about Rust shenanigans and they decided to try rewriting it in Rust. Said original employee who was writing it in C was not very happy about it originally, but he eventually came around and is now one of the most prolific contributors in the Rust ecosystem, generally speaking. But basically, I have a quote. So we ship Rust to redacted. I was talking with Yehuda last night about this. We ship Rust code to a redacted number of customer servers and have done so for a couple of years. There have been 2 crashes in those 2 years. One was due to a bug in Rust that we fixed. Another one was due to some silly shenanigans. The point is that I can literally enumerate all the crashes they've had. Again, this is like code that is being deployed to other people's servers they do not control under whatever kinds of conditions, and it's been super, super rock solid. And furthermore, this is another thing that I think is very interesting and another aspect that's cool about Rust. The employee who wrote the original Rust code has left, but we haven't found it tough to maintain, even for new employees with less Rust expertise. All of the bug fixes to this agent have been done by someone who primarily writes JavaScript and Ruby. So there's a number of smaller startups who I did not put on this list of production users, but one of the common things that people bring up is the Rust compiler being so strict means it's like a teaching tool. So I'm much more willing to hire someone that is relatively more junior because I know the compiler will check their mistakes. Whereas if I was writing C code, I would need to double check literally everything they do to make sure that there weren't as many problems. And I know that at least if it compiles, a certain degree of checking has been done. Obviously, I still have to review their pull requests, but it like helps give me more confidence. And furthermore, I can say, go take a weekend and play with these projects and they can learn more about systems programming. And so I see Rust in this way is attracting a lot of people who've traditionally not done systems, specifically because the safety net of the compiler makes them feel much more safe and nice that things will work. And so this is something that's very, very common. And so yeah, so Tilda / Skylight has been very happy production user for a very long time. It's worked out extremely well for them. The way that Yehuda puts it is, we are a 10-person team competing with a publicly traded company, and we still ship features faster and have customers in a viable business anyway. And a lot of that is due to how rock solid they use Rust and Java and Ruby and Ember basically as their stack. And they're like, all the technologies we've chosen have paid out really, really well. And then finally, the last production user I'd like to talk about is Firefox. So I work for Mozilla. As I said earlier, I don't do any work on Firefox, which is cool. I do a lot of traveling, and so when I tell people I work at Mozilla, the Firefox company, they're like, oh, that's cool, but I use Chrome. And I'm like, it's cool. I don't work on Firefox. I don't care. That's not my thing. I use Iceweasel because I'm on Debian, which is hilarious as like a Mozilla employee. I don't actually use the real build. If you know any of that history, it's terrible, and we're fixing it hopefully soon. But trademark, copyright, free, it's hard. Anyway, the point is so Firefox. The reason that Mozilla has invested so much in Rust, and we think of Rust as truly being a community project. Mozilla pays most of the people that work on Rust full time, but like we have about 40 people that are involved in Rust governance, and about half of them are Mozilla employees. So we still definitely are like the significant amount, but by no means are like in full control over Rust. But the reason that Mozilla puts all of this work into Rust and why Mozilla cares about Rust boils down to Firefox. So Firefox is about 4.4 million lines of C++ code, in my understanding. And if you look at the most serious of safety bugs, like security bugs, like visit this web page and someone runs arbitrary code on your computer bugs, they all boil down to C++ is a sharp tool, and you will get cut sometimes. And so there's this browser competition called Pwn to Own. I don't know if you've ever heard of it or not, but the vast majority of bugs that happen that are found during that particular program boil down to memory safety bugs a lot of the time. But also just in generally in Firefox, 50% of all bugs that have been filed against security stuff when we did the audit last were basically memory safety bugs. So Mozilla is interested in Rust as a way to twofold. So we want to improve Firefox, but at other time, there's this thing called Servo. This is the logo they're using currently. They don't have a real logo yet, but they also have a good sense of humor. So they got the Doge as their logo. But Servo, at the same time that we wrote Rust, we are also working on a browser rendering engine in Rust. And there's multiple reasons for that. One of them is that if you're writing a new programming language, a common tool, you want to make sure that your programming language is good. So you try to write programs alongside of the programming language to make sure that your language is good at writing actual programs. And of course, because you like your new language and you're working on this compiler all the time, one of the things that you do is you rewrite your own compiler in your own language, because that's, that way you can actually use it. But there's a danger there, which is that you'll make a language that's great for writing compilers, but not for writing other kinds of programs. And so what we did was we have a whole separate team of people that are working on just building a web rendering engine. And by rendering engine, I mean like WebKit or Gecko, not like Firefox in whole, but like the thing that determines what gets drawn on the page where. And so we've been rewriting one of those completely from the ground up in Rust, although it does use a number of C and C++ components that it wraps, but like the core of it is all in Rust and is slowly replacing those things as time goes on. But that is sort of twofold. The first one is to prove out Rust as a language and make sure that it works. But the second, I put this slide out of order. The second one is that like Servo is slowly moving its way into Firefox as well. So I guess I'll talk about that in a second because I want to show you these things. So one of the cool things about Servo is that it's massively parallel at all levels. So this is an example of a couple months ago of Servo rendering the Rust subreddit. And these, the colors on the boxes indicate a different thread that determined where that layout object needed to go. So there actually are like, we are using multiple threads on like every single level, and it demonstrates the kind of like parallelism that it has. But recently, there was this talk given about WebRender that's really, really cool. WebRender is this new technology that Servo has pioneered that lets you draw things on the GPU. And if you pay a lot of attention to browsers, you might say, well, Steve, browsers already do some stuff on the GPU. And my response is, go watch the talk on WebRender. It's actually like even more stuff on the GPU. But the point is that with WebRender, they haven't found any real web pages that don't render at hundreds of frames per second. And it's not so much that you want web pages to render at hundreds of frames per second. Like even gaming monitors don't actually give you that kind of resolution. But the point is that the rendering of the page will not be what makes it slow. So like if we make the web faster, that means we can do more with the web. And the web is free and open. And I love the web and want to use it for as much as possible. And so, you know, reducing the amount of overhead that it takes to like draw the web page is useful for enabling new things to happen with web technology. So they have several demos they use in this talk that I don't have time to show you, but basically boil down to if you create a specially crafted web page with 600,000 divs on it and then use CSS3 transformations to animate them into like a swirling vortex, that will run in 60 frames a second in WebRender, but it'll run at like a quarter of a frame per second on Firefox or like half a frame per second on Chrome right now. So there's some really, really interesting stuff going on with the performance aspect here. And as I mentioned a minute ago, we're basically moving components from Servo into Firefox. So if you download Firefox, well, I'm skipping ahead. That's my next slide. If you download Firefox today from firefox.com, if you're on OS 10 or Linux, there is some Rust code in there already. A very, 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 very tiny amount of Rust code, but it's there. Yes, that's actually the hardest part. Like, imagine what the Firefox build system looks like. Now imagine introducing a new programming language into that build system. It took a while. Windows is going to happen in a couple releases. There are some things, whatever, this is not a talk about the internals of Firefox. But the point is that we're sort of taking this two-pronged approach. One is where we take components out of Servo and put them into Firefox directly. So one of the patches that has not landed yet, but we're hoping to land relatively soon, is to replace the URL bar and all of its parsing and stuff that it does with Rust code. Another one is the styling and layout system. And so those components are like working their way into Firefox. And also new components that are relatively isolated are trying to use Rust first as a way of getting more Rust code into Firefox. But the idea is that sort of Rust will slowly eat Firefox from the inside, outside. I realize this is a metaphor. I didn't know which way it actually went, but whatever. The percentage of Rust code will increase. For various reasons. And then also in June, we're going to release a demo of Servo as a browser of itself. We're basically only guaranteeing that 3 or 4 websites will work well, but the idea is to collect telemetry on what parts of the web platform website to use so we know which parts to implement next. And the cool thing about that is it's going to ship with this project called browser.html. So basically, even the Chrome of the browser is actually a web page. So you can think of it as like no Chrome, but like a web page that has an iframe where the actual web page is inside, right? And what's neat about that is it means to customize your web browser. If this became a real production web browser someday, which is far from doing so, but if that were to be a thing, you could customize your browser using only HTML, CSS, and JavaScript. No need for additional complicated stuff. And so that's really, really neat, and I think that will enable a lot of people to do really cool stuff. Okay, so that is all the time that I have to share with you. Unfortunately, we did not get to go to lunch early because I actually talked a lot. I apologize. Thank you so much for having me, and I will be around tomorrow as well. So if you want to talk more about any of this stuff, please come find me. I will be the dude in all black, even though it's warm outside. Thank you.